Okay, so in this video, we're going to look at section 11.3 and 11.4, talk about the regression equation, and then we'll do a full hypothesis test for it as well. And so the regression equation is what we sometimes call as the line of a best fit. And so we're going to go ahead and look at this example here with the exam scores. So a random sample of 11 statistics students produced the following data. So they looked at the third exam score that was out of 80, and then their final exam score, which was out of 200. And they wanted to see if these were somehow related, and we could kind of predict the final exam score given students' third exam score. This is example 11.6 from the text. And here's the data that we have. So we have those 11 students here, what they got received on the third and then on the final exam here. And then we also have a scatter plot. And so we typically refer to the regression equation as the least square regression line, the linear regression, or the line of best fit. And so what we're trying to do is we're trying to find a line here that is pretty much closest to most of the points. And it doesn't necessarily have to go through any of the points, but we're trying to find that line that would kind of best fit these guys. And we write it as y hat is equal to a plus bx. And then our a is the mean of the y's minus b times the mean of the x's, where our b is given by this equation here, the summation of x minus x bar, and that's multiplied by y minus y bar, all over the summation of x minus x bar quantity squared. Our line always contains that x bar and y bar. That's a value that's fixed on there. And then here's another way to actually get our b from our equation here. So let me explain this a little bit. Kind of the gist of the idea is, so every line that we have has some errors. So the distance from the line to the actual value that's observed, we call that an error or a residual, or we refer to it as epsilon. And so the actual value y minus the predicted y hat is going to equal to an epsilon. And we use a little subscript of i's right here because we technically have 11 different values. So it's going to be specific for each one. And so we want to put a line in there that minimizes all of those errors. So we're going to fix our line right at the mean here, okay? So we find out what the mean is for all of our x's. We find out what the mean is for our y's. And that point is going to be where we fix our line. Now, there's a lot of different points here, but I'm just going to consider these two right here. Notice there's some error with that. There's residuals there. And so what the goal is, I'm going to teeter-totter this line a little bit. So, for example, if I were to rotate this counterclockwise, again, it's fixed at the mean, but if I were to turn it, notice that this residual here will actually get smaller. So that gets more accurate there. However, the other residual back here, that one is going to get larger. So the goal is to teeter-totter this line here. And we want the line where if I add up all of those different residuals, all of those different errors, I'm going to end up with the smallest number possible. And that's how we get that line of best fit. So we want the line with the least total errors. Okay, so here is the data. And we're going to run a 1var stats on both x and y. And if we run those, these are the mean values that we have. And then I'm just going to write our standard deviations. Okay. And I'm rounding to 2 decimals, but we're really using a lot more in our calculations. And these are going to be the columns that we want to extend out here. So we're going to want to do this for x minus x bar, y minus y bar, then the multiplication of those, and then x minus x bar quantity squared. And so I'm going to use my list to help me out with this. So I get a little bit savvy with the calculator, and I go ahead and input, and I get these values. So I'm going to go ahead and add downwards on this L5 where I'm multiplying both of those. And if I add them up, that's the summation. So I get about 394.09 or so. And then we get the summation of these as well. Of the x minus x bar quantity squared, we get about 81.64. And so my B is going to be the ratio of those two, which is about 4.83. And my A is going to be equal to 160.45 minus 4.83 times 69.18, which again is those means, and then we're plugging in our B value in for that. And so this is our linear regression, what we're going to call y hat in this case here. Now, that's a bit complicated. One way to do this is in our calculator. If you go under stats, you could actually run a linear regression here. Notice I put list 1 and list 2 into the calculator here. And if you go under stats, you're going to go down to linear regression. Now, there's two of them. There's one that looks like B plus AX, which is what we typically reserve for the algebra one. This one's a bit further down. It's going to be down at about number 8 or 9, depending which app or TI you're using. So make sure you're using the one that's A plus BX. And it's going to give us a whole bunch of information here, but notice it gives us our equation, our A and our B, and it even reminds us how to write it, just in case if we forget there. And ultimately, what we're going to be doing is running a hypothesis test anyways. So when you run a hypothesis test, it's going to be a linear regression t-test. It's going to give us all of these values as well. So everything that just running a linear regression gave us as well here. Okay, but we'll get into that. So typically when we do the hypothesis test, I'll run it and then I'll fill in some values after. One thing we want to talk about also is the correlation coefficient, which is our R. And this is a pretty ugly equation here to plug stuff into if we wanted to calculate this R coefficient. And what this correlation coefficient tells us is, again, think of the slope of it, whether it's increasing or decreasing, so it's positive or negative. But it wants to tell us how close everything is to a straight line. So those residuals get very, very small. They get closer to that line. And so an R of about 1 would be that it's close to a straight line increasing. An R close to -1 would be that it's close to a straight line decreasing. And if it hovers around 0, that means that there's really no correlation, really, that it's increasing or decreasing, and it's just kind of more scattered there. So our R is always going to be between -1 and 1. And so our calculator, when we plug it in, it gives us that value. R is 0.66, which means it's a positive correlation. And the question is that weak or strong? And so if we had something, in the 90s, like 0.98, that's fairly strong. If we have something on the lower end, 0.03, we know that's fairly weak because it hovers around 0. But 0.66, is that strong or not? That's really the question we want to ask. And to truly answer that, we're going to need to run a hypothesis test to see if that is strong enough, okay? But for now, we're kind of just saying if it's positive or negative. We will really only say weak or strong if it's, really high or really low. Somewhere in between where you're unsure of, we really got to run a test to decide that. And one neat thing about our R value is we could actually use that to get our B for our equation. So instead of having to do that other calculation with that larger table, we talk about the slope as change in y over change in x, so the variability in that. And in statistics, when we talk about variability, we're talking about the standard deviations. So our slope is given by the ratio of those two. Again, change in y over change in x, but we multiply it by that correlation coefficient R. So this is a nice shortcut way to do it if you are going to be doing stuff by hand. And then there's also R squared, which is the coefficient of determination. And this tells us the percent of variation that the dependent variable can be explained by the variation in the independent variable here. So our R squared is 0.44, which is about 44%. We typically write this as a percent. And again, this comes from the calculator. Make sure your diagnostic is on to get the R and the R squared value. So we say about 44% of the variation in the final exam, which is our Y, can be explained by the variation in the third exam, which is our X here, if we were to use the best fit regression line. So let's look at 11.4 here, where we're actually going to go ahead and just run a test, a full hypothesis test. And when we run the hypothesis test, our null is that rho is equal to 0. So that's Greek letter R. So rho, and the alternative is going to be that rho is not equal to 0. And again, this has to do with our R value, our correlation coefficient. Remember, if that's about 0, that means there's no linear relationship. And so that's what P equals 0 is saying. So in words, we would say the null hypothesis is the correlation coefficient is not significantly different from 0. So that means there is not a linear relationship or a correlation. Okay, so that's one way to remember it. If R is close to 0, we're saying that there's not that correlation. And technically, we are doing a T-test for this linear regression, and this is the formula to get the test statistic, and our degrees of freedom are given by n minus 2. Very, very important in a test. Correlation does not imply causation. So we can't say that someone who scores well on the third exam will definitely get a high score on the final if there is that correlation. We're just saying there's a relationship, but it doesn't mean doing one will cause the other. So let's look at the example of, again, that exam scores comparing the third exam, which is out of 80, to the final exam, which is out of 200 from these 11 students. And let's do our 4-step hypothesis test. So we're going to go ahead and conduct a full linear regression test here. And so the first step, let's do the null and the alternative. And again, we're looking at rho, and equals to 0 means that there's no linear correlation. Rho is not equal to 0 means that there is a linear correlation. And in this case, we're going to let the claim be the alternative because we're trying to see if we can predict that the final score, could be seen from the third exam. So we're trying to see if there is a linear correlation. So a bit subtle, but that's really the claim in this case. So step 2, really we're going to do our stats and data. So we're really just putting in list 1 and list 2 here. So the third exam being list 1. And our independent and our dependent being list 2 here. And you could run a linear regression under the stats menu, and it's going to give you all the stuff we need. Our equation, again, make sure your diagnostic is on. You could find that under mode, or you could go under your catalog to turn that on. And it's going to give us all our values. It didn't give us an alpha, so again, a typical alpha value that could be used is 0.05 when not given. That's pretty standard. And so let's look at our third step here. And technically, this is a T distribution, and it's going to be a two-tailed because we're trying to see if there is or there isn't here. So there is our alpha halves, and then those go with the T critical values there. And if we run this on our calculator, if we do a linear regression T-test, again, it's going to give us all of the values again. So it still gives you your equation and everything that was done from the linear regression. So I would probably just hold off on writing on doing the linear regression and just go straight to the test, and then you could fill that step in afterwards. Make sure that you are using the appropriate selection here, though. So we want the equals, or I should actually say this is going to be the not equals case, because it's always what's in the alternative there. Okay. Now, technically, we're just seeing if there is or is not a linear relationship. That's what most textbooks use. However, if we were to test less than or greater than, we could really be testing if there's a negative relationship or a positive relationship using those. But we're going to stick to just the equals and not equals case. So our test statistic is 2.66, and our p-value is 0.0262. And then here we have our degrees of freedom, again, given by n minus 2, so it's going to be 9. We could have got our t critical values if we do an inverse t, again, area to the left with the degrees of freedom. So that's 2.26. And again, positive and negative because it does end up being a two-tailed test in this case. And here's our alpha. So this is nice that we could compare our t-scores to one another to see where something falls, or we could compare the area. And we actually see that the p-value is less than alpha, so it's going to be contained within that critical region. And technically it's p half, so you could have it on both sides shaded there, but it's going to be within. And so our fourth step is we are going to have our discussion and conclusion. And so p-value is less than alpha, so we reject the null, which means you do not reject the alternative. And in this case, the alternative was our claim. So we would say there is sufficient evidence to show there is a linear correlation between exam 3 and the final. Again, since the alternative is my claim, I am allowed to use language like support. And again, we're not saying that if you do well on the third exam, you're going to get a good score on the fourth exam. We're just saying there's a relationship. There's other factors, and it's possible that might not happen.